Hi, my name is Elaine Young. I'm going to start off with a quick summary of my poster, and then I will jump into some more of the details later on in the video. The goal of the project overall is to test the accuracy and reproducibility of remote rupture maps and slip measurements. The work presented on this poster focuses on a small area of the 2019 Ridgecrest earthquake sequence. So to start off with, each of the authors used the lidar imagery in a variety of different visualizations to map the rupture. So we then convert those mapped shapefiles to rasters to avoid any bias from different mapping styles. So mapping really continuously versus smaller segments. And then we use those rasters to compare between the mappers and to the published maps. When we do our comparison, we add a 1 meter buffer to either side of whichever map is being compared. And that allows us to account for differences in line placement. So mapping the top of a fault scarp versus the bottom of a fault scarp, that doesn't get penalized, but mapping like a different feature does. We then compare each of our rasterized maps to the Duras and Ponti maps to get the number of overlapping pixels. Future work will include exploring different buffer widths as well as a variety of methods for comparing the maps, and we will also analyze the entire rupture instead of just the area presented here. Thank you so much for coming to my poster. Please feel free to contact me if you have any questions. Okay, so jumping into more of the details. We're going to start with the types of visualizations that we used. So we had 5 that we preferred. The first is a DEM with a dynamically scaled color ramp. We found red easiest to look at, so that's what's shown here. And the cool thing about this DEM with the adjusting color ramp is as you zoom in and out, the full range of the color ramp is displayed. So at large scales, you see really large scale variations, but then as you zoom into an area that's really flat, rather than staying one color, that color ramp adjusts, and so you get to see a lot of the details as you zoom in and out. We also found it useful to add a slope map on top of the DEM to help highlight the scarps. The slope map that is shown here is transparent on top of that DEM, and it's colored so that anything with a slope greater than 40% is just black. And that makes it really obvious where there are steep features in the landscape compared to where it's more flat. We used 3 different ways of viewing hillshades. The first is the default hillshade that's generated in GIS. It's not actually the most useful way to view the landscape for this rupture because it doesn't illuminate all of the features very well. So another one that we tended to use quite often was a sun azimuth of 45 degrees and a lower sun altitude of 30 degrees. This puts the sun lower and at a more perpendicular orientation to the rupture and does a good job illuminating most of the features. The last thing that we did is changing the vertical exaggeration in the hillshade. This really helped highlight the small scale features in the landscape that are difficult to see otherwise. So it was a helpful way to go back in our mapping and fill in the gaps. To compare between mappers, we used the rasterized version of their rupture maps, and we compared each mapper and each published maps 1 meter raster against all of the other maps rasters with a 1 meter buffer added. We compare our 3 maps against published maps from Duras et al. And Ponti et al., both 2020 publications. For the Ponti et al. Map, we break out the subset of their lines that's derived from field data, and we also compare it to their entire map. We also compare against all of Ponti's lines with a 1 meter buffer and a 2 meter buffer to see if adding a wider buffer improves the agreement. Adding a 2 meter buffer does improve the agreement that we see between the lines.